Welcome back, everyone. Today, we're going to be looking at something I think is really fascinating, and that's the potential for smaller AI models to tackle these complex math problems, sometimes even outperforming the giants out there, like OpenAI's models.
Yeah, it's a real shift in thinking. I think, for a while, bigger was always better in the AI world, but this research from Microsoft really suggests that might not always be the case.
Yeah.
Their paper, rStar-Math, Small LLMs Can Master Math Reasoning with Self-Evolved Up Thinking, introduces a system that combines small language models with a really strategic approach to problem solving.
We've got that research paper right here, along with some other related articles ready to break it down.
Right.
So what is the core problem that this research is trying to solve?
Well, I think the challenge lies in the way that a lot of large language models, LLMs, approach problem solving. They rely very heavily on what we call system one thinking.
Okay.
These fast, intuitive responses is great for a lot of tasks.
Right.
But when you get into that really complex mathematical reasoning, it can lead to errors. Yeah.
Especially when multiple steps and deeper logic are required.
Yeah, it's like trying to juggle too many mental calculations at once.
Exactly.
Easy to drop a number and mess up the whole answer.
Exactly. And that's where system two thinking comes in.
Right.
That slower, more deliberate approach, like carefully working through a proof.
Right.
StarMath aims to kind of implement this kind of thinking in smaller language models, or SLMs, using a method called Monte Carlo tree search, or MCTS.
Now, MCTS, for our listeners, is a technique often used in game-playing AI.
Yes.
Where the system kind of explores various potential moves and their consequences.
Right.
So how are they applying that to this mathematical reasoning?
Well, StarMath guides the SLM through a more strategic step-by-step process.
Okay.
And I think one of the key innovations here is how it generates and uses training data. It's not just about feeding the model a bunch of equations.
Right.
It's about quality over quantity.
Okay.
They use a method called code-augmented chain of thought data synthesis. Okay, so let's break that down. Chain of thought prompting is a way to get these LLMs to kind of explain their reasoning in a step-by-step manner.
Right.
But what's this code-augmented part all about?
This is ingenious, really.
Okay.
So the model is trained to generate not only natural language explanations for each step of a math problem, but also executable Python code that matches those explanations.
So the AI is writing its own code to essentially double-check its logic.
Precisely.
That's a really clever way to catch errors early on.
Exactly. And by ensuring that these steps are both logically sound and executable, the researchers can filter out that low-quality data and ensure that the model is truly thinking deeply, not just mimicking patterns.
Yeah, it sounds like they're building in a level of self-verification into the training process itself.
Absolutely.
But how does the system actually get better over time? So they're ensuring this high-quality training data, but how does the system actually learn and improve from that data?
Yeah, that's where this self-evolution aspect comes in. StarMath starts with a basic SLM. And improves it through 4 rounds of iterative training. And each round focuses on generating increasingly challenging and diverse data, pushing the model further.
It's like the system is setting its own increasingly difficult tests, learning from its successes and failures as it goes.
Exactly. And to guide this learning process, they use what's called a process preference model, or PPM. Instead of relying on, rough estimates of how good each individual step in a solution is. The PPM is trained to judge the relative quality of different reasoning paths, helping the system zero in on the best strategies.
So it's not just rewarding the AI for getting the right answer. It's also rewarding it for thinking effectively.
Yes.
For choosing smart paths to get there.
Precisely. And the results are quite impressive. StarMath significantly improves the performance of various SLMs, even those with relatively few parameters on challenging math benchmarks. We're talking about benchmarks like MathAIM, that's a high school math competition, and even college-level problems.
So it's not just simple arithmetic. It's tackling some pretty high-level concepts here.
Absolutely.
How does it compare to the performance of the larger, more resource-intensive models out there?
Well, that's the remarkable part. It achieves accuracy comparable to, and in some cases, even surpassing OpenAI's O1 models, which are significantly larger. It really challenges that assumption that bigger is always better in AI.
Yeah, it's like finding out that a compact car can outperform a race car in a complex course just by being more strategic and efficient. What implications does this have for the field of AI development?
Well, I think it has the potential to democratize access to powerful AI tools. Right now, developing and using large language models requires massive computational resources, which really limits access to a select few.
It creates a bit of an AI has and have-nots situation,
right? Yeah, exactly. StarMath shows us that smaller, more accessible models can achieve incredible results with the right techniques. This could open up a whole world of possibilities for individuals, researchers, smaller companies, anyone with an internet connection.
Yeah, it could really level the playing field, allowing people to kind of innovate and solve problems using AI that previously only these large organizations could access.
Exactly.
That's exciting. And I imagine there's some very specific fields that could benefit greatly from this kind of development.
Absolutely. The potential applications are vast. I mean, think about education, for example. Imagine students having access to personalized AI tutors that can adapt to their learning styles and help them understand complex concepts.
Or in scientific research, where researchers could use these smaller models to analyze data test hypotheses and accelerate discoveries without needing access to a supercomputer.
Exactly.
That's amazing.
And it's not limited to math.
Right.
The researchers believe that this deep thinking approach can be generalized to other reasoning tasks like code generation, or even tasks that require common sense reasoning.
This is really opening up a whole new world of possibilities. But as with any powerful technology, there are bound to be some potential downsides or concerns. Did the researchers address any of those in their work?
Yeah, it does feel like there's always kind of a flip side to any technological breakthrough. Were there any limitations or areas where rStar-Math struggled?
Well, one area that they highlighted was problems that require visual understanding.
Okay.
Like geometry.
Right.
The current system is primarily focused on textual and symbolic reasoning. So tasks involving visual or spatial elements are still a bit of a challenge.
It makes sense. It's like trying to describe a painting using only words.
Exactly.
Lose some crucial information.
Yeah, but even with that limitation, the researchers demonstrated rStar-Math's ability to solve a wide range of problems.
Okay.
From algebra and calculus to number theory, even some Olympiad-level problems.
It's impressive to see that kind of versatility in a model that's comparatively smaller than these giants out there.
Right, and that's really the key takeaway here.
Yeah.
This research challenges our assumptions about the limitations of smaller AI models.
Right. It suggests that with the right approach, these models can achieve remarkable results, opening up new possibilities for AI development and accessibility.
It's a shift in thinking, moving away from the bigger is always better mentality towards a more strategic, efficient approach.
Exactly. And I think that's a really exciting direction for the field.
Yeah.
You know, this research is just the beginning.
Right.
I'm eager to see how this deep thinking approach can be applied to other domains beyond math to unlock even more potential.
It's an invitation for researchers and developers to get creative think outside the box.
Absolutely.
Find new ways to enhance AI's capabilities without relying solely on massive computational power.
Exactly. This research is a reminder that innovation can come from unexpected places.
Yeah.
And sometimes the most powerful solutions are the ones that embrace efficiency and strategic thinking.
It's a great note to end on. This has been a fascinating deep dive into the world of smaller language models and their potential to really tackle this complex problem solving.
It's been a pleasure.
And to our listeners, we encourage you to check out the full research paper, rStar-Math. Small LLMs can master math reasoning with self-evolved deep thinking. It's linked in the show notes. Let us know your thoughts.
Yes.
What other applications can you envision for this kind of deep thinking approach? What does the future hold for smaller, more accessible AI models?
Join the conversation and let's explore these possibilities together.
Until next time, keep exploring, keep learning, and keep diving deep.